Welcome to Section 5, Lesson 11. In the previous lesson on function composition, we chained two functions in sequence to build a new pipeline. Today, we cover the simpler way to combine two functions, arithmetic. Adding, subtracting, multiplying, and dividing two functions f and g produces four new functions whose rules are built by applying the corresponding arithmetic operation to the outputs of f and g at each input. Function arithmetic complements function composition and gives a complete toolkit for building complex functions out of simpler pieces. Today we lock in the four arithmetic operations, the domain rules for the combined functions, and the procedure for evaluating combinations symbolically and at specific inputs. First idea on the board. The four arithmetic operations on two functions f and g produce four new functions f plus g, f minus g, f times g, and f divided by g. The rules for the new functions are for x plus x equals f of x plus g of x minus g of x equals f of x minus g of x times g of x equals f of x times g of x, and f divided by g of x equals f of x divided by g of x. The arithmetic happens on the output values at each input, not on the function rules as algebraic objects. Second idea. The domain of any combined function is the intersection of the individual domains of f and g, with one extra restriction for division. For addition, subtraction, and multiplication, the combined domain is just the set of x values that are in both the domain of f and the domain of g. For division, the combined domain additionally excludes any x value where g of x equals 0 because division by 0 is undefined. To evaluate a combination at a specific input, compute f of that input, compute g of that input, and apply the arithmetic operation to the two output values. To work with the combination symbolically, write the rule for the combination as the arithmetic combination of the two original rules. Often the symbolic combination simplifies into a more compact rule that reveals the structure of the combined function. Today's two worked examples cover both the at-specific input evaluation and the symbolic combination procedures. The four arithmetic operations on two functions f and g produce four new functions whose rules combine the outputs of f and g pointwise at each input. F plus g of equals f of x plus g of x, f minus g equals of x minus g of x, f times g of x, f of x times g of x, and f divided by g of x equals f of x over g of x. Here is the domain rule. The domain of any combined function is the intersection of the individual domains of f and g, the set of x values for which both f and g produce valid outputs. For addition, subtraction, and multiplication, this intersection is the complete domain of the combined function. For division, the combined domain additionally excludes any x value where g of x equals 0 because division by 0 is undefined. Step 1 in evaluating a combination at a specific input. Compute f at the input, getting a specific number. Compute g at the input, getting another specific number. Apply the arithmetic operation to the two numbers to get the value of the combination at the input. The procedure is mechanical and uses only basic arithmetic on the two output values. Step 2 for symbolic combinations. Write the rule for the combined function by performing the arithmetic operation on the algebraic expressions for f of x and g of x. Simplify the resulting expression where possible. The symbolic rule is the cleanest description of the combined function and lets you evaluate at many inputs efficiently without going through the two-step at each input procedure. Step 3. Identify the domain of the combination. Take the intersection of the individual domains of f and g for any of the four operations. For division, additionally find every x where g of x equals 0 by solving g of x equals 0, and exclude those values from the combined domain. The exclusion can be expressed in interval notation by removing single points or sub-intervals from the otherwise common domain. Here is the first worked example. Given f of x equals 2x plus 1 and g of x equals squared minus 3, compute f plus g of 2, f minus g of 2, f times g of 2, and f divided by g of 2. Step 1. Compute f of 2 and g of 2. F of 2 equals 2 times 2 plus 1 equals 5. G of 2 equals 2 squared minus 3 equals 4 minus 3 equals 1. The two output values at the input 2 are 5 and 1 respectively. Step 2. Compute f plus g of 2. Apply addition 5 plus 1 equals 6. So f plus g of 2 equals 6. The combined function at input 2 produces the output 6. Compute f minus g of 2. Apply subtraction 5 minus 1 equals 4. So f minus g of 2 equals 4. Step 4. Compute f times g of 2. Apply multiplication 5 times 1 equals 5. So f times g of 2 equals 5. Step 5. Compute f divided by g of 2. Apply division 5 over 1 equals 5. So f divided by g of 2 equals 5. We need to verify that g of 2 is non-zero, which it is at value 1. So the division is well defined at this input. Step 6. Sanity check by computing one of the combinations a second way using symbolic combination. F plus g of x equals 2x plus 1 plus x squared minus 3 equals x squared plus 2x minus 2. Evaluate at x equals 2, 4 plus 4 minus 2 equals 6. Match. The two procedures agree as expected. So the four combinations at x equals 2 are 6, 4, 5, and 5. The big lesson from this example is the at each input evaluation procedure. Compute f and g separately at the input, then apply the arithmetic operation to the two output values. The procedure is mechanical and works for any combination at any input where both f and g are defined and the additional constraints for division are met. The cross-check with symbolic combination is a useful sanity test on harder problems. Here is the second worked example. Given f of x equals x plus 3 and g of x equals x squared minus 4, write the symbolic rule for f divided by g and identify the domain of this combination. Step 1. Write the symbolic rule f divided by g of x equals f of x over g of x equals x plus 3 over x squared minus 4. The numerator is f's rule and the denominator is g's rule. Step 2. Identify the domain. The individual domains of f and g are both all real numbers since both are polynomials with no internal restrictions. The intersection is therefore also all real numbers, but the division has the extra restriction g of x is non-zero. Step 3. Find the zeros of g. Solve x squared minus 4 equals 0. Factor the quantity x minus 2 times the quantity x plus 2 equals 0. So x equals 2 or x equals negative 2. These are the values where g vanishes and must be excluded from the domain. Step 4. Express the domain in interval notation. Start with all real numbers and remove the two specific points x equals 2 and x equals negative 2. The result is the union of three open intervals from negative infinity to negative 2, joined to from negative 2 to 2, joined to from 2 to positive infinity. Each interval uses round parentheses around the excluded boundary points. Step 5. Verify by computing the combination at a specific allowed input. At x equals 0, f over g of 0 equals 0 plus 3 over 0 minus 4 equals 3 over negative 4 equals negative 3/4. The output is well defined because g of 0 equals negative 4 is non-zero. Step 6. Sanity check at an excluded input. At x equals 2, f over g of 2 would be 5 over 0, which is undefined. So x equals 2 is correctly excluded from the domain. Same at x equals negative 2, f over g of negative 2 would be 1 over 0, also undefined. Domain restrictions correctly identified. So the symbolic rule is x plus 3 over x squared minus 4, and the domain is the union of negative infinity to negative 2, negative 2 to 2, and 2 to positive infinity. The big lesson from this example is the symbolic combination workflow with explicit domain analysis for division. The numerator simplification is sometimes possible if the numerator and denominator share a factor, but in this example they do not, so the combined rule stays as a clean rational expression. The domain analysis is essential for division. Always solve the denominator equals 0 equation and exclude the resulting values. 3 mistakes that catch every algebra student during their first weeks of function arithmetic work. Each one is fixable with a small explicit habit applied on every problem. First mistake: skipping the zero denominator restriction when computing the domain of f over g. A student writes the symbolic rule for f over g and stops there, treating the domain as the intersection of the two individual domains without identifying the zeros of g. The fix is to always solve g of x equals 0 explicitly when working with division, and to remove those values from the intersection. The zero denominator restriction is a separate step from the intersection step and applies only to division. Second mistake: confusing the arithmetic operations and applying the wrong one to the two outputs. A student computing f times g of 2 adds the two output values instead of multiplying them, getting f of 2 plus g of 2 when the correct value is f of 2 times g of 2. The fix is to read the operation symbol carefully. A plus sign means add, a minus sign means subtract, a multiplication symbol or implicit juxtaposition means multiply, a division bar or slash means divide. Match the operation symbol to the arithmetic operation used. Third mistake: confusing function multiplication with function composition. A student looking at fg of x interprets the notation as f composed with g, so f of g of x, when the correct interpretation is f of x times g of x. The composition uses the small circle notation f circle g of x, while the multiplication uses simple juxtaposition f g of x or explicit times symbol f times g of x. The two operations are completely different and produce different results. The fix is to memorize the notation conventions: small circle for composition, juxtaposition or explicit times for multiplication. Function arithmetic appears constantly across physics, programming, finance, and statistics because building complex quantities from simpler component functions is one of the most common modeling moves in all of quantitative work. 4 broad sectors below. In physics, the total energy of a moving object is the sum of its kinetic energy and its potential energy, both of which are functions of position. The total energy as a function of position is therefore the sum of two component functions. Similar sums appear for total force from multiple sources, total flux from multiple contributing fields, and total cost in many engineering optimization problems. Function addition is the foundational operation for these aggregations. In programming, total system cost is often computed as the sum of per component cost functions, with each component contributing its own cost as a function of usage or capacity. Total runtime of a multi-stage algorithm is the sum of the per stage runtime functions. Total memory usage is the sum of per data structure usage functions. Function addition gives the aggregated cost or resource function in each case with the same arithmetic on functions logic. In finance, profit margin is computed as profit divided by revenue, where both profit and revenue are functions of business activity. The margin function is therefore a function division of two underlying functions, and the analysis of the margin's behavior depends on the analysis of the two component functions. Similar ratios appear for return on investment, cost to income ratios, debt to equity ratios, and many other financial metrics. In statistics, combining estimators or test statistics through arithmetic is a foundational technique. The difference of two means estimator subtracts one mean function from another to estimate the difference between two populations. The pooled variance estimator combines two sample variances through a weighted sum. Function arithmetic is the explicit machinery, and the resulting combined estimators have well understood properties that follow from the arithmetic structure. 3 things to take with you from this lesson today. Function arithmetic is one of the foundational ways to build complex functions from simpler component functions, and it appears constantly across physics, programming, finance, and statistics for aggregating, comparing, and ratioing component quantities. First, the 4 arithmetic operations on two functions f and g produce 4 new functions whose rules combine the outputs of f and g pointwise. F plus g of x equals f of x plus g of x, the same pattern with subtraction, multiplication, and division. The arithmetic happens on the output values at each input, and the new function inherits the input-output structure from f and g. Computing the new function at any input is a matter of evaluating f and g separately and applying the arithmetic operation. Second, the domain of any combined function is the intersection of the individual domains of f and g. For addition, subtraction, and multiplication, this intersection is the complete combined domain. For division, the combined domain additionally excludes any x value where g of x equals 0, because division by 0 is undefined. Always solve g of x equals 0 explicitly when working with division and remove the resulting values from the intersection. Third, function multiplication uses the juxtaposition or explicit times symbol notation f g of x or f times g of x and means f of x times g of x as a product of the two output values. Function composition uses the small circle symbol f circle g of x and means f of g of x as a chained two-step evaluation. The two operations are completely different and produce different results in general. Memorize the notation conventions carefully to avoid confusing them. Function arithmetic plus function composition together form the complete toolkit for building complex functions out of simpler component functions, and recognizing which operation is at work in any given expression is one of the central craft skills for the rest of the course and into calculus. Coming up next, the lesson called Section 5 Marathon, where every function concept from Section 5 is applied back-to-back on a mixed sequence of problems covering definition, notation, evaluation, domain and range, transformations, composition, inverse, even, odd, piecewise, and arithmetic combinations. The marathon is the natural completion of Section 5 and the practice format that builds the speed and pattern recognition needed for harder course material later in the year.